good morning. This is the second part of CPU scheduling. In this, we are going to discuss about the Peterson solution. It is a busy waiting solution and it is a two-process solution. As you have seen in the previous one, the strict alteration, it works on the basis of turn variable. Uh, in Peterson solution, along with the turn variable, there is also a flag variable which defines that the intention of a process P1 or P2 to willing to execute the critical section. If P1 sets its flag value as true, then it means it want to execute its critical section. Turn basically defines that it's the turn of P1 to execute or P2 to execute its turn. So basically, it happens is like that. First, a process flag that it want to execute the critical section, like here. Then if that and then it checks that whose turn it is. So if P1 want to execute critical section, then P1 sets the flag 1 as true, and then wait for then check for the turn, that if it's his turn, if turn is equals to 1, then it can access the critical section. But if turn equals to like 2, which means process 2 has its turn, and then it will check that process 2 want to execute critical section or not. If process 2 does not want to execute critical section, then process 1 can execute critical section. So first, for we are using it for process I, and we setting j as a j as not of 5, which means if like process I is 1, then j is 0. Then if process I want to execute critical section, then it will set flag of I as true here in point B. Then it will set the turn equals to I. Turn equals to is means it will set it turn equals to is means that if P1 want to execute, matlab, like if P1 uh, comes first, then it will execute first. Like if P1 and P2 both want to execute the critical section, and if P1 comes first, then it will allow to execute critical section before P2, which is signifies which is the reason for the C point here, turn equals to I. Then there is a while loop which will check that if flag of j is equals to true, flag of j equals to true means it that process P2 want to like the another process want to execute critical section. If other process does not want to execute critical section, then we can execute critical section. Turn not equals to j means process whose update turn will go first. Turn not equals to j means basically if both process want to execute critical section, then that process which come first will execute critical section. And flag of I is set to false. Not true. Here should be I guess false. If false means after executing set of I equals to false. Means he has completed his execution and does not want to access critical section again. So yeah. The limitation of Peterson solution, that it only works for two process solution and it works on busy waiting. Busy waiting basically means that like if P1 is executing critical section and P2 also want to execute critical section, then it will waste CPU cycle while executing the while loop in point D, busy waiting. So another problem is Decker's solution. Decker's algorithm. It works similar to Peterson solution, but uh, and it guarantees mutual exclusion, progress, and bounded waiting. So here is a code for Dyaker's algorithm. If you want to study, you can do it on your own. Second is synchronization hardware support. Support special atomic instruction to solve critical section problem. This is a hardware solution. Before we discussed was a part of software solution, software based solutions. So synchronization hardware first is like if a process basically why we what is the basic need of synchronization or synchronization solution is basically that to avoid interrupts. If a pro like if two processes are accessing a shared resource and one gets preempted in between, then it will and then the is then the final output will be depending upon the order of execution, or while you can say inconsistency in data will be there. So first problem is like when a P1 or any process want to execute critical section, first thing was that it disable all the interrupts. Like if P1 want to execute a critical section, then it entry section is made such that it disable all the interrupts. And then when P2 completes its execution of critical section, then it will enable all the interrupts. So if when interrupts are disabled, then no preemption of a process is done, and if no process is preempted in the critical section, then the synchronization is maintained. But problem here is that enabling and disabling interrupt can only be done by kernel, or basically when a system is in kernel mode, then it can only disable or enable interrupts. Second is TSL. TSL instruction or test and set lock. It is a busy waiting solution. Hardware synchronization requires special instructions, and it is a multi-process solution. TSL lock. The syntax of a TSL lock is such that it returns the current value of lock and always set the lock to true. It basically if whatever the input or the parameter is given to the TSL, it will always set the lock to true and return the current value of the lock. Well, basically first it return the current value and then set that value to true. Well, return the old value and then set the value of lock to true. So if the value of lock is true, is set by the P1. If P1 set the value of lock to true, then if any process want to enter the critical section, sorry, let's just scrap that idea. It's like, okay, first the value of lock is false, which is the base condition. If process P1 want to use TSL system, then it will provide the parameters, like a true variable or whatever, or the value of lock. And what TSL does is it returns the value or original value and set the value to true. So initially the lock variable is false. So when the TSL is applied to a false variable, it returns the earlier original value false and set the new value to true. If any other process want to do that the same thing, then it will return true and set the true. So lock is always set to true. So while critical section, so there will only one process will enter in the critical section, because only one will disallow or negate this statement. Only the first process will execute. The P1 will allow to negate this statement because only P1 will return the false. And after that, the after execution that of one process, it will set the value of lock to false. So it works like that. If like this is lock false, and if P1 want to enter critical section, it will pass this value in this function of TSL. So what TSL does, it returns false and set lock to true. So when it's set lock to true, now any other like process P2 want to access the lock variable, it is already true. And if when it passed from TSL, what happened here is that TSL returns now true, and value of lock is again always set to true. Set to true. So while executing this statement, only P1 will able to negate this statement, and P2 will doing a busy waiting or a continuously executing this loop if for infinite amount of time or until P1 executes this statement. TSL enables mutual exclusion progress but does not validate bounded waiting. Oh, swap instruction is like you provide a lock along with a key and it swaps those value of lock and key. But these instruction are atomic in nature, and swap instruction guarantees both mutual exclusion and progress but does not guarantees bounded waiting, just like TSL. Priority inversion. Any busy waiting solution suffers from priority inversion. It is a preemptive based priority scheduling. So what happened here is that like a low priority process is currently executing in a CPU, and it is executing the critical section. And when a high priority process PH comes and want to execute the same critical section, so what happened that in critical section only one process will be there. So algorithms such as Peterson solution, Decker's, TSL, swap will deny as the high priority process to execute the critical section as high priority it will result in a kind of a deadlock because lower priority process cannot execute as there is a higher priority process, and lower priority process is currently executing when preempted was executing critical section, so no other process can enter the critical section. So a priority inversion takes place here, which changes the priority of low process to a higher process and a higher process to a lower process, so that the lower priority process, which is in the which is executing critical section, can came out of critical section, and then the original high priority process can execute or completes its execution. Yep, here it is. Let PL, a low priority process, arrives, runs on CPU and are executing critical section. The higher priority process PH arrives and preempt PL from CPU, and PH is executing on CPU. Now PH completes its execution without entering the critical section. अगर वो critical section में नहीं आएगा तो कोई दिक्कत ही नहीं होगी, लेकिन if PH high priority process can try to enter critical section but cannot. If PH want to execute the critical section part of a problem, but it cannot. Why? As PH cannot enter critical section as PL is already present in critical section. To move PL out of critical section, PL needs to run on CPU, but PH cannot allow lower priority process to run before PH. High priority process does not allow low priority process to run before it. So the system is in kind of a deadlock. It is also known as live lock. Yeah, what happened in deadlock is there is not enough resources to execute, but in live lock there is are enough resources to execute, but the situations are such that none of the process can execute. As as it is written here, in deadlock process are in block state, but in live lock process is in ready or a running state, ready and a running state. To solve this, we can priority inheritance as priority switch between PL and PH until PL exits the critical section, and now again priority is reverse. So to solve this live lock, PL become high priority process and PH become low priority process until that low priority process came out of critical section. After that, again the priority switches. Yeah. Um, so now we will go look over non-busy waiting or blocking mechanism. So what is like if a process want to execute critical section and cannot enter, so what to avoid busy waiting, we can send that process to sleep. So basically, non-busy waiting means that process which is unable to enter critical section goes to sleep until the process that is executing in critical section came out. So it saves CPU cycles uh, by avoiding executing the same while loop again and again. Sleep First is sleep wake. It is a non-busy waiting. It is OS based and it is a multi-process based solution. So it suffers from inconsistency and deadlock. Okay. This is a modified producer consumer through wake up, sleep and wake up. Um, why we say that it suffers from inconsistency and deadlock? See, what happen is like that. Initially, the buffer is full. So what happen is that producer goes to sleep. Just before producer execute this statement of sleep here, it gets preempted and consumer start consuming. Now consumer consumes like some like there is a buffer of n. Let consumer consume like 1 or 2 packets. So what happen is like that now the value of buffer is changed. it is less than 1, but buffer is less than 1, and now the consumer gets preempted and producer start executing. So the last statement that producer now the producer which is now the statement which producer is gonna execute is the sleep one. But now that condition is not here, like now the value of count is less than n. So here the producer goes to sleep for forever, uh, uh, as value of producer goes to sleep for forever, because he thinks that buffer is full, but in reality buffer is not full. Now what happens is that as consumer goes on consuming, now the buffer becomes zero. As buffer becomes zero, as buffer becomes zero, now the consumer goes on to sleep. Consumer thinks that buffer is empty, which is the reality, and it will not wake up the producer because it already it already reduced count minus minus one, uh, uh, and it does not execute this statement of wake up producer because at that time the producer is already waked up. So it's I will just do a little bit better this way, like, yeah, here. So initially, like buffer is full, buffer is equals to n, and producer is so producer is executing here. I mean, like producer is executing better. We just want to draw this. It's like now the producer is executing like buffer full. Now it is executing. Now it's the next instruction gonna execute is sleep. But here preemption happen, or consumer start executing. So what happen is that at this state, the producer is actually wake. Now what happened? Consumer start consuming, so it will like consume, like currently the value of buffer is n. So n minus 1 happen after that consumer consume 1 unit, and then consumer tried to wake up P, but P is already wake. As P is already wake, so nothing will happen, and consumer might consume anything or like end it. But now P1, not P1, like P, the producer again wake up. Now producer again wake up, and producer cannot again check that statement of buffer equals to full, cause it is already executed that statement. Now the producer will execute the sleep statement. As producer executes the sleep statement, it goes to sleep on assuming that the consumer will wake up, but consumer will not wake the producer, as consumer not wake up the producer, as he thinks that buffer is not full, and he already wake the producer yeah, before it's done. Now the producer is at sleep, and consumer thinks like keep on consuming, and when the buffer becomes zero, now the consumer also goes to sleep. Now both of the consumer and producer goes to sleep, no work is done, result in a kind of a deadlock. Inconsistency, same producer think that buffer is full, but in reality it does not, it isn't, so result in inconsistency.